Hello, this is Dr. Christy Patton-Lukes, Chemical Engineering Professor at Missouri S&T. We are continuing our study of Chapter 5 on thermodynamic processes and cycles, and we are specifically looking at refrigeration cycles at this point. We've been talking about vapor compression refrigeration. Let's look at some variations. The cascade cycle is one of these. Basically, the issue is that there are limits on the operating pressures of the evaporator and the condenser because of our temperature difference that we're looking at, TH and TC. When those are too large for us to make this work with any fluid reasonably, then one thing that we can do is operate two different refrigerators. So the heat output from one drives the heat input to the other. This is called a cascade refrigeration cycle. Now I do want to pause here to take a moment to point out that on our refrigerators, whenever we draw these, if you notice that my connecting the dots is going counterclockwise on my refrigeration cycles, this is traditionally the way we draw these. And also when you looked at either the pH or the TS diagram, refrigerators, when you connect the dots, they always go counterclockwise. Engines, when we draw those, connecting the dots, this is not a convention, this just is the way it works out, they always end up going clockwise on TS or pH diagrams. And so we traditionally draw these so that the arrows are oriented the other direction. So that's one thing that people do that makes it kind of a nice, easy visual hint that you're looking at either a refrigerator or a heat engine. So let's look at the cascade cycle a little bit more closely. Typically what happens is you make a choice, you know how much cooling you require in your evaporator for your refrigerator, and you know what your TH is. When you do your design, if those do not provide a rational design, then we can choose two different fluids with an intermediate temperature here. So TH for cycle 1 that provides our cooling is going to be the QC for cycle 2. And we'll want a slight delta T between these, typically on the order of, say, 10 degrees between those two temperatures there. And we're going to do this so that I get a reasonable performance for cycle 1. The heat output is the heat input to the other one, and a reasonable performance for cycle 2. Now you can do a cascade with 3 of these, okay, if that's what it takes. But this allows us to have a larger delta T between my surroundings and what it is I am trying to cool. Another form is the absorption refrigeration. Now the kernel of an idea from this one is basically, you got a refrigerator and I have to put work input to it. Well, if I have to put work input, couldn't I put a power cycle on it to provide that work input and just size it exactly right so that it just drove the entire thing, and then I wouldn't have to do anything? Okay, the world would be better. Well, sort of. But playing with that idea got us to absorption refrigeration. So I can take heat in at an elevated temperature and at a reduced temperature and then reject it to the surroundings, and I can improve my performance. This is absorption refrigeration. If you look at the idealization on this one, for a Carnot refrigerator that absorbs heat at TC and rejects it to the surroundings, the work would be TS minus TC over TC, multiplied by the Q for the cooling. And then if we're providing that work from a Carnot engine that's at TH, which is higher than the surrounding temperature TS, then we can get that QH is W times TH over TH minus TS, okay? We're just playing with the Carnot efficiency definitions. And then when you use those two simultaneously and eliminate the W, you end up that the ratio of the QH to the QC is going to be TH times TS minus TC over TC times TH minus TS, okay? So this gives me an amount of heat that I would be able to do by cooling based on how much I had to do for my heat source. What this cycle ends up looking like, now this is drawn, and this is why I say that traditionally we try to draw refrigerators going counterclockwise and power cycles going clockwise. This is kind of both, and they are both drawn going clockwise as if they are a heat engine. Anyway, so we basically have our refrigerator side over here drawn backwards. Okay, so I've got my evaporator, and I have, this is going to replace the compressor. Okay, going to condenser and then back to the Joule-Thomson valve. Okay, now then, my compressor, instead of just using a compressor, let's just replace it with an entire power plant, okay, albeit small. So now then, let's look at this over here. So this is my pump. So I'm going to bring my material in. I'm going to heat it. Now I'm not going to typically have like a fired furnace or something. I'm just going to use a heat exchanger and then use a couple of different heat exchangers here, but I'm going to use this regenerator, which is going to drive the temperature feed into the condenser. And then that material is then going to go through a valve into an absorber. Now the reason we're not going to be able to analyze this fully at this stage is because the absorber, well, the absorber is actually, it's a chemical phenomenon there due to the way that materials give off or take in heat when they are mixed. And so this has different combinations of chemicals that are being combined and releasing heat to the surroundings as a result. So it's a little bit above what we can do in this course, but absorption refrigeration is going to be a better use of resources, but it's a lot more equipment to manage. However, if you had to do something where you were doing a lot of refrigeration, so maybe an ice cream factory or something like that where you had a lot of cooling that you needed to do, this starts looking like a more rational thing to do. And so, again, this is going to require information that we will learn about in thermodynamics too. So basically, the difference between them is how we do the compression. So to the right was the vapor compression refrigerator. To the left was the compression via a heat engine. But the refrigerant is a vapor in the evaporator, and it's absorbed in a non-volatile liquid solvent at the evaporator pressure and relatively low T, and heat given off in this process is discarded to the surroundings. This is thermo 2. We're not ready for that at this stage. The liquid solution from the absorber is passed to a pump, which raises the pressure to the condenser pressure, and then the heat evaporates the refrigerant from the solvent. The vapor goes from the regenerator to the condenser, and the solvent goes back to the absorber, and all of the energy is conserved there, which optimizes all of your temperatures. Usually we use a low pressure steam as the source of heat for that regenerator. Most of the time, they use water as the refrigerant and lithium bromide as the absorbent. So water works as the refrigerant as long as you are above the freezing point of water. If you need lower temperatures, you're going to use ammonia, and then the solvent typically would be water at those conditions. Another combination is methanol as the refrigerant with polyglycoethers as the absorbent. And these usually have absorption heat ratios of QH over QC of around 2.5. One last topic on refrigeration is the heat pump. Now, we mentioned this earlier. A heat pump is a reversed heat engine, which is a refrigerator. These are using refrigeration-style equipment to heat something. So a lot of times, depending on what part of the country you live in, you may have a heat pump instead of an air conditioner and a heater. And it operates as QC is going into the house during the summer months, and QH is going into the house during the winter months. So in winter, the heat is absorbing heat from the surroundings and rejecting it into the building. The refrigerant evaporates in coils, either underground or in the outside air. And then in condensation, the heat is transferred to either air or water to heat the building. The compression has to be such that the condensation temperature is higher than the building temperature in all operating conditions. So in the summer, the heat pump works as an air conditioner. The flow of the refrigerant is reversed, so heat's absorbed from the building and rejected through underground coils or to the outside air. It still is going to go through the compressor in between those and the Joule-Thomson valve on the other end of those. So it's really just a matter of changing the flow patterns to make it work as a heat pump. So this concludes this lesson. In our final lesson for this chapter, we will be looking at liquefaction. Thank you very much for your time.